Right. So greetings, ladies and gentlemen. We are continuing with section 7, looking at a computer memory system. Previously, we introduced memory, covering fundamental concepts of what memory is and the importance of its interaction with the processor and how that really gives us the computing functions that we enjoy. We especially emphasized the ideal requirement that the processor have regarding memory, issues of speed, especially issues of size, issues of even power consumption, and discuss that it is impossible to actually have a single memory technology that delivers all those requirements. And therefore, what we intend to do in this session is to look at how practical memory systems use a hierarchy of technologies, like a hierarchy of memory technologies to mimic, or to give an illusion of ideal memory system, meaning one that is fast, one that is large, one that supports all those or many of those ideal requirements that we discussed in the previous session. So we want to do that by looking at an illustration that comes from the library system, by looking at how a library system actually works. It gives us an idea of how hierarchy is used in memory to guarantee or to provide an illusion of ideal memory system. So there are a number of levels basically that we can discuss in terms of how a library works. Of course, we won't exhaust all the layers, and all the options, but we have simply picked core ones which are aligned with what we want to illustrate. Firstly, starting with the authors, being the individuals that actually create knowledge, and their knowledge is captured in the form of books, right? So similarly, just as authors, create knowledge, or they, they produce knowledge which is captured in the form of books. We discussed early on in the course that computers really are data processing machines. They are machines which are fed data either in the form of raw data or in the form of instructions that they need to process, to either extract meaning or to accomplish a certain specific task. So similarly, we have the concept of I/O, especially input for this scenario, through which we have those interfaces that allow data to come into a computing system. And of course, in the illustration of the library, the data that authors generate, the knowledge that they generate is encapsulated in books, and then in our computer system, we have data, we have data which can really take many forms. It can be data being the operands that your computer system is going to process. For example, in terms of image processing, those images that are fed into your computer, for it to either apply machine vision, techniques to either extract a certain feature or to process your audio or to process your documents or your video. Or it can be data in the form of instructions that are fed to your computer system for it to run. We are speaking of your WhatsApp, your all the applications that we download and install in our systems to actually give them certain functionalities. So authors will generate that knowledge captured in the form of books, and the books will actually be bought and brought to the library, but normally the way libraries works, books are not brought directly to the shelves where people who visit the library can actually, pick them and use them. Rather, books are bought and they are put in a basement, where the librarian, based on the kind of customers, he or she serves, can pull books from the basement and, place them on the shelves. Either you have shelves for history, shelves for mathematics, shelves for the sciences, and shelves for a range of areas and topics that people who visit the library might be interested in. So, so that basement, in a way, basement storage inside your library can be understood as or typifying your secondary storage, in your computer system, like your hard disks, either your HDD or your SSD, that provide permanent large-scale storage facility for your data. Like we said, either raw data in terms of operands to be processed, or the applications that are downloaded on your phone, on your laptop, or any computing device that you are using. Okay. But of course, the born human machine, follows a load store architecture, which entails the processor working from the registers, whether it's instructions or it's operands, they're not really processed or worked upon whilst in your storage memory. Instead, just as it happens in the library, the books have to be brought from the basement and they are placed on the shelves, respective shelves, like we said, and all the shelves are actually, numbered. They have, indexes or indices, that are used to make it easy to identify the shelf, the books that are located on the shelves. So similarly, books are brought from the basement and they're placed on the shelves, and then a visitor in the library, then depending on what they want to do in the library, okay, they want to study about the history of the Zulu warrior charter, right? Perhaps write a research paper about him, okay? So obviously they will go to the literature shelf, okay? Which of course will contain many books on many, books basically, or biographies about many people, right? Um, of course, then they will have to page through that specific, like the specific shelf, and zoom into maybe historical literature about, um, I mean, African warriors, and they go specifically um, to maybe Zulu genre, and they 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 find a number of books on the segment of the shelf, written about, Chaga or Shaga by several authors. Okay, then what they do, um, one, you can either pick a particular book from the shelf, for example, Chaga by Thomas Mafolo. You pick the book, and then you go sit on your chair, all right, and then you read the book, and to conduct your research. But depending on really the task that you are undertaking in the library, normally just picking one book, uh, I mean, might not suffice, because you want to read about Chaka from multiple perspectives and be able to compile whatever paper you want to compile. So uh, instead of picking one book, sitting on your chair, reading the book, and realizing that, oh, okay, this one speaks about a Chaga, basically from perspective one. Maybe let me find another perspective. About the warrior, meaning you need another book, right? So you go back to the shelf, you uh, put back the one that you were currently holding by Thomas Mafolo. Why? Because you don't have space, on your chair to stack books. Put it back, you pick another one, and then you go sit on your chair and you read it. All right. That's option one, which of course it's not very efficient in terms of usage of resources, your energy. You, it's going to require you to do many several visits to the shelves, okay, which of course wastes time and also wastes energy, and therefore it's not efficient. Rather, you want to identify a desk in the library, okay, and it's nicer when the desk is actually um, I mean, a desk given to yourself. You work on the desk alone, or if you are actually doing a research project together, you're three or four, you all sit on the desk, okay? You are four processors, and you have one desk to yourself. You go to the shelves, you pick books around the theme that you want to research on. And when you pick the books, now, you are not going to pick one book, right? You will pick maybe two or three, four books around the theme that you are really interested in. And then you pick them, you place them on your desk, and then you consume them. You read through them. You page from this book, put it down, you take another one, put it down. At times, you will realize that the books you have on the desk are not able to answer a particular question that uh, that you have. Okay, what you do? Stand up. You go to the shelves. Okay, you pick one book. Not really. Okay, because uh, you are wasting energy. You won't pick one book. You pick also additional what, three or four or five. Okay, around the same theme that you are looking into. So this is equally how memory works, okay? Data has come into your system via your I/O interfaces, okay? And this data is stored in your secondary storage of your computer system. We are referring to your HDD, okay, your SSD, and for the processor to start working on this data, if it is a program, an application, for your processors to start running this application, your WhatsApp, your browser, your Office, I mean your um, um, Adobe Reader, you know, the data, the application has to be loaded into main memory, and this is your RAM, okay? And from your main memory, and the way the processor will load, I mean, data to bring it closer for it to start processing it, is that it will, it will load it in blocks and into its cache memory. Then from your cache memory, it can be loaded into the registers, which are very, very, very close to your processor now, and they are the fastest processor, storage available. Then the machine cycle can actually, happen right in there, where if it's a program, it is has been loaded from memory, it is stored inside your instruction registers, it is decoded, the operands are pulled either from the register file, sometimes from main memory, but cached within your cache memory. Results are produced, they are written to registers and persisted on your cache memory, sent back to your main memory, and then depending on the nature of the application, then persisted permanently on your storage memory. So the important point here that we want to emphasize is the concept of locality, which says the accesses that we do, to the storage memory, into main memory, or to main memory into cache memory, are influenced by the concept of locality, which says if you visited or you picked a book, okay, by Thomas Mofolo, written on Chaga, you are very likely to pick the book next to it. It's probably a book on Chaga written by another author, okay? Or it's a book not necessarily on Chaga, but on the Zulu history written by another author. So you are likely to revisit spaces that you have visited before, okay? So because of that principle, okay, we say it makes sense, therefore, not to go to the shelf or not to go to main memory and all you retrieve is one memory word, okay? Because you're wasting memory cycles. Rather, go to main memory or go to your storage memory, your hard drive. You know exactly what you're looking for. You're looking for a book, by Thomas Mofolo on Chaka, but don't simply retrieve that book alone. Why? Because in the subsequent cycles, you are highly likely to want to access another book next to it. So therefore, go to memory, storage, or main memory, and retrieve a block of words, okay, that are around the particular one that you're looking for. Then you bring that block into the cache, you catch it so that in the subsequent clock cycles, uh, when you want to access them, they're already closer to you. Okay. So that's the idea, really, the concept of locality. So from storage, we pull pages. Okay. We pull pages around what we are looking for. Even from main memory, we don't pick one memory word. Rather, we load a block of memory, which is like multiple words. So, for example, when you have an instruction like load word into a register from a certain given address, what's going to happen in effect is that it's not only that word which is going to be loaded from memory, okay? It's not only the word at the given address that is going to be loaded from memory into your cache. Rather, several, blocks around it will also be retrieved, pulled into your cache. Of course, in terms of loading from your cache into your register now, you are going to load only the one that you're looking for into the register, okay? Into the register. So you have locality of reference, which says you are highly likely to want to access something that you have accessed recently, okay? And then you have locality, like a spatial locality, which says you are likely to visit spaces next to the space that you have visited recently. Hence why we say, don't just pull one, pull a block. So at times it happens that, when the processor now, being the visitor in the library, right? You have pulled your books from the shelves and you've placed them on your desk, typifying your cache memory. And obviously, your desk is smaller than the shelves. The shelves are smaller than the basement. And so as you page through the books you have on your desk, you may find that, there's something that you're looking for which is not available in the books that you have on the desk. That's a cache miss, okay? And therefore, because of a cache miss, you have to incur the penalty of doing what? Of standing up from your desk, pausing what you're doing, and going to the library shelf, looking for an additional book that can respond to your need at that particular point in time. But also, you can go to your shelves and you find that this book is appearing on the library system, is available in this library, but it's not on the shelves, meaning it's probably where in the basement, right? And obviously, accessing things from the basement is much more costly in terms of time and even the procedure, okay? It takes more red tape to access books that are still stored in the basement and bring them to the shelf. And then from the shelf, then you can, pick it, place it on your desk. Okay. So that's the catch miss, and the standing up, having to retrieve what is missing. That's the miss penalty. At times, you will find that it's completely not available. Okay? It's not there in the basement. It's not there in the main memory. It's not there on the in the cache memory. Either maybe it's there, then the device containing it has been unplugged from your computer system, or it's been deleted. Okay, so you have the miss penalty. for a time you're looking for it, and it's right there on your couch. Okay, it's right there on your couch. You have a couch heat. Okay, so the way we retrieve blocks of data from main memory, and and even the way we design our couch, the size, and even the way we arrange the books, even on the couch, okay, should be such that it makes it easy, quicker, for us to access a word, okay, uh, from the couch, and also make it easy so that we are more likely to have hits than misses, because I mean misses are misses are expensive. Okay, misses are expensive. So, and I mean, at times, also depending on the design of your catch, like we said, obviously your catch is smaller than your shelves, so it does get full, right? It does get full, and when it's full, you have to replace books and make space for new books so that you can, I mean, bring the new books that you want. So we will discuss issues of catch replacement policies that can be adopted, or I mean, how catches um, manage, I mean, its resources in terms of um, creating space for new entries when it is full, um, so that it retains its performance and of um, giving the high hit rate and minimizing visits to main memory. Of course, the same thing happens also to main memory. It does get full, because you don't have unlimited number of, or size of RAM. Therefore, it can only accommodate a certain number of applications, data. Once it gets full, there has to be replacement, of applications back to storage, and bringing of new data into memory, especially if that particular application at that particular point in time has been given priority by the processor, by the processor. So those are the catch replacement policies that we will discuss. But hopefully, you see how, although you have, I mean, fewer registers, right? And then you have a smaller cache, right? Which of course is built from faster memory technology. But because of this management of, I mean, register memory, cache memory, main memory, and storage memory, the computer system is able to give the user, an end user, okay, the system developer, an illusion that they actually have access to, I mean, large, fast memory. All right, how? Because, I mean, entries are cached on your table, right? Entries are cached on a table. When the table is about to get full, we make space, we bring them closer, we work on them, and as far as the processor is concerned, whenever it needs stuff, most of the time it finds them. It finds them without having to go all the way to the basement. So this is the idea, which is captured also using bits pyramid that we discussed previously, of having most expensive, smallest capacity memory, even fastest one at the top. Okay, these are your register memory. Then below it you have your cache. Below it you have your main memory. Below it you have your secondary storage. Memory. Okay, so we use a mixture of different device types. For trade-off. Most expensive at the top, but smallest. Least expensive at the bottom, largest, slowest. Okay. So this is the same thing here, showing the position of your hard drive, of your main memory, and your cache being, actually directly connected to your processor chip and sitting even on the same same die. Okay, same IC. And here it's a recap of the differences in performance and cost across the representative technologies for cache being your SRAM, main memory built in DRAM, and then your virtual memory, which is like your storage memory being either SSD, which is faster, more expensive, and then your HDD being slower and least expensive. All right. So here we have just examples of register memory for modern processors that we find in modern devices like our laptops, our phones, and either, classed according to generic registers, special ones, floating point ones, or themed ones. Okay. So for example, your Intel Core i7 has 16 generic general purpose registers, okay, of varying sizes, 8 bits, 16 bits, 32 bits, or 64 bits. And then it also has special purpose registers for the single instruction, multiple data pipelines that allows one instruction, which can be applied to a large data set. So the way that instruction can be made to run faster is by deploying it across a themed node, which takes one instruction and then divides the data set into small segments and then deploy each of that data segment across the instruction. So it could be your 128-bit, long bits registers to 6, 512, Obviously here we are speaking of vector processing. You want to add vectors, multiply them, subtract them. So these are the registers you can use for that purpose. All right. Yes. So here it's more or less the same thing explained. Differently using a different diagram, but it's still the same idea. The important point here to note is the fact that the card can actually have multiple levels, which will differ in terms of size. Level 1, smallest, fastest. Level 2, slightly bigger, slightly less fast. Okay. Level 3, bigger, and even somewhat slower, but still faster than access to your main memory. Why? Because of the technology used to construct it. So this is a screenshot, for example, from my old laptop showing the cache profile on my laptop, having 33 kilobytes of level 1 cache, 56 kilobytes of level 2 cache, and then 6 megabytes of level 3 cache. See that in terms of the technology used to construct them, the technology is the same, but the more size you design into your cache, the more slower you make your cache to be. Why? Because I mean, you are putting more components and more locations. So if you are searching for a particular word, it means you have to traverse more entries, as opposed to having something which is small and having fewer entries, and that makes it even faster. So this is it about our cache memory. A little extra detail here on important features of your cache memory. Also, a screenshot from my old laptop. This is the level 1 cache. It's, of course, it's internal. It's directly connected to the processor. The size is 32 kilobytes. And this one is a data cache, right? This one is a data cache. And then you have another 32 kilobytes level 1 cache being instruction cache. So in the MIPS, the data part that we've been discussing, where you see instruction memory and data memory separated, that separation can also be achieved via, the cache, right? Because the processor does not directly go to main memory to access words. Rather, the memory in that case is actually the cache memory. So you have your instruction cache, which caches instructions. Then you have your data cache, which caches the data that instructions are going to process. And then of course you go to your level 2, level 3, but you still have this concept of the separation of data and instruction, of course, which you know by now that it helps to avoid a situation whereby the performance of your processor is bottlenecked by the bus between your processor and your memory. Having a instruction cache and data cache allows your processor to be able to read from both the instruction cache and the data cache at the same time, or even write to them at the same time, without the single interface being a bottleneck, right? So we are going to stop here, and in the next segment, we will discuss how we can actually construct larger memory chips from smaller, cheaper ones through the technique of interleaving, either high order or low order memory interleaving. Thank you, guys. Let's meet in the next segment.